I don't know if you can hear it, but if I put my finger there, so this thing is vibrating up and down based upon the frequency of our electrical supply, which is 60 hertz. So ideally, so the ideal frequency here is 60 hertz. That's what we're going to see how close we can get. The string, which I put somewhere. Now, it does not have, the amount that we actually use for vibrating does not have to be the same length as what we use for measuring. The linear density should be the same regardless of how much string is used. So now comes the coordination issues. Excellent. And also, if this is not tied properly, this will come undone during the middle of the lab. All right, there should be a granny knot there. Hopefully this is a little bit more stable than I usually do. All right, and I just need to get this down in here. All right, so I'm going to be hanging mass on the string here, and hopefully that mass will be in equilibrium. If it's in equilibrium, then the weight of that hanging mass should be equal to the tension. All two forces that are equal in magnitude, canceling each other out. So I got more string here than I need, so first let's get something tied here. Any Boy Scouts in here? Girl Scouts? Who learns to tie knots?
I used to know. I don't know if I'll know how to do it anymore. You're asking for a bow one. I haven't tied one in a couple of years.
The adjustable hitch knot probably quite better dexterity. All right. Hopefully that's going to be good enough. Now, the amount of mass I really need in order for it to vibrate in one of the harmonics, we will find out. All right, and I definitely don't need that. Now, we are also assuming that the string is massless. We assume an ideal string, and we assume that this will be more stable than that apparently was. All right, so I want the string to be basically straight on, so I had to adjust the pulley so that it was not coming onto the pulley at an angle, and just that side over there too. And also I want the string to be level. And so I guess on the side here, do I need to take this up or down?
It looks pretty close. I can't really see a horizon.
Okay.
Looks not bad.
That's fine. All right. So as I plug it in, you can notice that the string's starting to vibrate. It's not quite at a harmonic here, but we have what's looks like the formation of an antinode here and two nodes over there. Now, do I need to add more mass or less mass? Well, that if I push down on it, well, that definitely looks better to me. So I need to add more mass. If I do less mass, there's the second harmonic. Hit the third harmonic there briefly. So how much more do I need to add? So I'm going to add 200. Probably more than I need, but ooh, that's looking pretty decent there. The question is, can you see a little bit off? I don't know how well you can see from over there, and then from that side. Okay, so it is a little bit off here. The fact that it's not too steady. Am I a little bit too light or a little bit too much? If I pull down, it gets worse. If I go up, oh, that actually seemed to have stabilized it. All right. We have a first harmonic there. It's just a little bit off. Let's see, if I add that, what does that do? It's more stable. I got a node here. I got a node here. I think we'll call that good enough right there. All right, so I have a first harmonic. It's this pattern right here. Notice that the drawing here represents, this is the part that's going back and forth very quickly. It's the antinode, and it looks just visually like it is in both places at once. It is just moving so fast that it only appears to be two places at once. In the video, this is another lovely thing about it, the frame rate of the camera I was using was 60 hertz. This is vibrating to 60 hertz, so basically you don't see it moving at all because it's taking still shots, basically the time it takes for it to come back around and get to the exact same spot. Like the anti-grav helicopter, I don't know if you've seen that, but it doesn't. You don't see the blades moving because the frame rate of the camera matched how long it took for the blade to go from here to here, which is where the other one was. So it looked like all the blades were standing still. And just for posterity, there's the vibrating string right there. All right, so let's do some math. It's going to be beautiful. This is going to work out. This is going to be the one that works.
It'll be the first time in history.
That's right. So we got, this is the vibrating length right here. This is the length, big L, that I have over there. So we need to measure that distance. That looks like I went to the top of the pulley, 81.3, it looks like. So L, 81.3 centimeters, or in meters. I think I heard that said. And all right, so we now have big L right there. So the wavelength, which is 2 times L, would be 2 times 0.813 meters. Because for the first harmonic, that was half a wave. So 1.626 meters. That's going to be the wavelength. tension. This should not have been moving much, if at all. So this was stayed relatively still. And so the weight of this should equal the tension. And so I have a 500, a 200, and a 20 gram mass here. So I have 720 grams hanging. So the hanging mass was 720 grams, which is how many kilograms?
0.7.
So what was the tension?
This multiplied by 9.8.
9 point what?
807.
We're actually doing a demonstration, so what's the number for here?
0.798.
9 point.
Yeah.
798. All right. So the weight is mg. So that's 0.72 kilograms times 9.798 meters per second squared. And this should be equal to the tension.
7.05456 newtons.
7.05456
56
units.
newtons.
All right, so we got all the data there. Let's let the magic happen.
Dr. Fox, you have a question?
Really quickly, so that F of T is force
That's the tension in the string.
of the tension, and then little f is
Frequency, yes.
Okay.
Yes.
Cool, I wrote that down wrong.
So the speed of the wave should be the square root of the tension over the linear density. And our tension, we just figured out, 7.05456, 7.05456 newtons, divided by the linear density, which we figured out over there, which is 0.00073085. And that's kilograms per meter. So what is the speed of the wave?
You got 98.24735 meters per second.
Yeah. Because clearly, the square root of a newton over a kilogram per meter is a meter per second. We've known that for a while. It actually is, it works out nicely, but instead of having to work through that, just its speed, meters per second. I assume you did the its speed, it better be meters per second. That's why we put things in kilograms and meters, so that we don't have to worry about trying to interpret what that is. All right, so we know the speed of the wave using the generalized formula, but we also know we're dealing with a standing wave here, so that should be equal to the frequency times the wavelength, or wavelength times frequency. So that equals frequency times the wavelength. And the wavelength we calculated over here. So that's frequency times 1.626 meters. So the frequency would be the speed divided by the wavelength, or 98.24735 meters per second, divided by 1.626 meters.
60.42.
Say it one more time.
60.42.
60.46. I might actually cry in front of you. This is incredible. Units?
Hertz.
Hertz.
Let's see what that percent error is. And this is being recorded for all to see so that it can be shown that in physics, you can do a live demonstration that actually works out incredibly well. So the percent error is the difference between what we got and what we were expecting, divided by what we were expecting, and then times 100 to get the percent form.
0.46. No, it's in it. 0.46.
0.46 divided by 60. You were looking strangely. Did I make a mistake? Are you about to crush my soul?
No, I'm just trying to figure out where you got 0.46 and not 60.46.
It's 60.46 minus 60. The numerator is the difference between the
Gotcha.
values we're comparing.
Gotcha.
Comparing.
.77. Oh, it's .766666666. Percentage.
Yeah, percent. 0.76 repeating percent, under 1% right there, live in front of you. You were there when it happened. Wow. I've done this where it's been 40% off. That's so nice to see. If you take this class, for several semesters, you'll recognize how special this is. All right. Questions? Ashley?
So it could like contribute to that 0.76 percentage error. Like what could have went just a tiny bit wrong?
All right, so the things that would be a little bit off, the mass that I had hanging on the end, I limited myself to just what I had right here. That if I were doing this in a proper lab, then I would have, pennies or paper clips or something like that. I could attach them to it until I got perfection.
Okay.
The other one is the mass of the string. Even though I tried to get as precise as possible, every measurement is a rounded off. So with that low of a percentage, it could very well be, maybe this was 1.72 instead of 7.3 or 7.4 instead of 7.3.
There's also a little bit of mass that's added to those hangers every time we measure them on the. It's always like a little bit, like there's always an extra little bit. On it.
And also the string has mass.
Yeah.
Now at the lower harmonics, it seems to have less impact, but when you get to greater harmonics, the mass of the string starts to have more of an effect. And if Ty and Marina's eyesight is a little bit off, maybe it's not perfectly level. But whatever errors there are, it did not seem to have a huge impact, or they all canceled each other out. All right, other questions? I'm gonna need to go get, 2 banana plugs. While I'm doing that, what I'm gonna do is I'm gonna hook this up. I hope, last time I tried this in front of a live class, I wasn't quite getting it right. Is if I change the frequency, or do I need to turn the frequency up or down and keeping that mass on there to get a higher harmonic? That was the first harmonic at 60 hertz. Is it below 60 hertz to get the second harmonic or above 60 hertz? So that is the question, and I need 2 chords. I'll just let the recording roll. All right, frequency up, frequency down. Did you have a guess?
I guess. Couldn't you theoretically do 5